Welcome to the Crazy Hat Chemist. So another video in bonding and molecular structure here. We're getting closer to the end of this entire unit. So let's get moving. Bam! So today we're going to be talking about sigma and pi bonds. And notice the sigma symbol right above the word sigma and the pi symbol right above the word pi. Okay, sigma bonds are single bonds and they are between s and p type orbitals. It's when a head-to-head overlap occurs within the same plane or along that same axis of the atoms being bonded. Okay, so here are two s-type orbitals. Notice that they are atomic orbitals. Notice that the s-type orbitals are spherical in nature. Okay, and that's what we're going to do is we're going to combine them together and we're going to get a sigma bond that's a molecular orbital. Okay, now we have two p-type orbitals right over here. Okay, we're going to overlap these and then we're going to have a sigma bond which is a molecular orbital of these two. Now we can have a s-type orbital and a p-type orbital and we can overlap the two of these and we also have a sigma bond here which is a molecular orbital. Notice that we are overlapping the orbitals in a head-to-head contact, kind of like if you have a train wreck. The two trains are on the same train track in the same plane and the trains collide together and that would be a sigma or a single bond within the same plane. Okay, now after a sigma bond is formed, some molecules, but not all, some of them can form a pi bond. And the pi bond is when you have a double bond or a triple bond. This could potentially occur. Pi bonds are between two p orbitals that are above and below the plane of the sigma bond and thus inhibit rotation around the axis, unlike a sigma bond. A sigma bond can rotate and double bonds and triple bonds cannot rotate because the pi electrons are above and below the plane of the sigma bond. So let's give you an example of a pi bond here. I got two different p atomic orbitals. These are going to overlap to form this pi bonded molecular orbital above and below the plane of the sigma bond. I'm not showing the sigma bond here. Okay, so notice that line is showing where the sigma bond would be located. That would form first before any pi bond would form. All right, so this would be a double bond. A double bond has one sigma, one pi. Okay, now I'm going to have a set of p orbitals and another set of p orbitals. So I got two sets of p orbitals. I'm going to first have to have a sigma bond and then I'm going to have two sets of p orbitals. Okay, and that is the plane of the sigma bond, just like before, that head-to-head overlap of orbitals. That's like a train wreck, right? And now I'm going to have a pi bond set. There it is like that. Okay, that is going to be a triple bond. Okay, so before I carry on, I'm going to show you some molecules which describe this here. This is a sigma bond. Actually, this region right here that I'm holding on to, that is a sigma bond right here. The two black ones are carbons, the gray ones are also sigma bonds, and then the white ones are hydrogens. But this here is a sigma bond. Notice that these atoms can rotate. So rotation can occur within a sigma bond. So these atoms would most likely be like this type of structure right here, because these hydrogens would be too close to each other, proximal to each other, and then it should look like that. Okay, so there is rotation around that single or that sigma bond. That's a head-to-head overlap of orbitals within the same plane. Now, if I were to take a single bond, a sigma bond of which I'm holding on to, and then overlap some p orbitals above and below the plane, this is a double bond. A double bond has a single bond and a set of pi orbitals above and below the plane. And so you should see that with this molecule, I cannot rotate it. Okay, I cannot, the rotation is inhibited because of the pi orbitals above and below the plane. So this is a double bond right here. Okay, let me show you one more here. And this is going to be a triple bond right here. So notice that you first form this sigma bond that is right here, and then you have two sets of pi orbitals, p atomic orbitals above and below the plane of the sigma bond. Okay, so again, there's no rotation that can occur with this because it's inhibited by the pi orbitals above and below the plane. Okay, I'm going to give you another example here, and this is with benzene. And you should see that there are sigma bonds, and then there is a set of pi bonds. So this is a double bond. Okay, and this is showing how benzene itself can have delocalized electrons, and that is that you have this whole set of pi orbitals above and then a whole set below. And there's no rotation in this molecule. It's a very special molecule, benzene it is. Okay, all right, so we've got much more to do, so hang on and don't go away. Okay, so a little bit of a summary of these here. So if we have a single bond, the type of that bond is a single bond. The bond order is a 1 because it's a single, right? Hopefully that makes sense. How many sigma bonds are within a single bond? 1. How many pi bonds are within a single bond? 0. The bond length is relatively long, and the energy to break that bond is very low, relatively. Okay, now if I were to compare that to a double bond has a bond order of 2, just like a double is a 2, right? If you are in baseball and you hit a single, then you go to first base. If you hit a double, then you go to second base, okay? So the bond order here is 2. There is one single bond, that is one sigma bond, and one pi bond. So you should see that the sigma and the pi sum up to the bond order. That's 1 sigma plus 1 pi equals a bond order of 2. Just like in the single bond, 1 sigma plus 0 pi equals 1. Okay, the bond length and the bond energy is intermediate, that of the single bond and the triple bond. Here's the triple bond. The triple bond has a bond order of 3, and it has 1 sigma and 2 pi. Again, the 1 sigma plus the 2 pi is equal to a bond order of 3. The bond length on a triple bond is very short, and the bond energy to break a triple bond is very high, again, in relation to a double or a single. Okay? In looking at the molecular orbital theory, okay, which we're not going to go into much detail at all, but the bond order is determined by 1/2 of the bonding, the sigma bonding, and the sigma anti-bonding orbitals, okay? So if you ever get into that molecular orbital theory, you can actually determine the bond type from the molecular orbital theory by looking at the bond order. So it lets you know the stability of that type of bond. If you get a bond order of 0, then that molecule doesn't exist. So this is why helium is not diatomic and it is monoatomic, because the bond order would be 0. If you get a bond order of 0.5, that's 1/2, then that could be a molecule. It's not very stable. But if you get a bond order of 1, that's a single bond. A bond order of 2, that's a double bond. A bond order of 3, that's a triple bond. Bond orders of 4s don't exist. Okay? So we're going to determine the number of sigma and pi bonds in H2. So what you're first going to do is draw the Lewis dot structure for hydrogen. Pretty simple. Hopefully you should get something like this right here. So we're going to count the sigma bonds and the pi bonds. Now that's a single bond between the 2 hydrogen atoms to form that hydrogen molecule, and it has 1 sigma and 1 sigma and 0 pi. That's why it's a bond order of 1. Okay, now we're going to determine the number of sigma and pi bonds in oxygen. That's O2. Again, you need to draw a valid Lewis dot structure for O2, and there is a valid Lewis dot structure. Now this has a double bond in it. So how many sigma? 1. How many pi? 1. So that is a double bond, has 1 sigma and 1 pi. All right, let's do one more here, and then we'll continue with the larger molecule, and that's trying to take a look at nitrogen. That's N2. Notice I've chosen diatomics here. It doesn't matter if you choose diatomics or not. But nitrogen, you're going to do, again, a valid Lewis dot structure of nitrogen. Okay, and this is the valid Lewis dot structure of nitrogen. Notice that the nitrogen molecule has a triple bond there. Okay, and that is 1 sigma and 1, 2 pi to form that triple bond. 1 sigma and 2 pi, that's a bond order of 3. That's why it's a triple bond. Okay, hopefully that makes sense there. Okay, so those are very simple examples. Now what we're going to do is we're going to expand this out into a larger molecule. Here's a larger molecule of aspirin. So acetylsilic acid. So acetylsilic acid. Okay, aspirin. Here is aspirin, acetylsalic acid. Okay, and we're going to count this. So you're going to come with me here on this. You got 1, you got 2, you got 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So how many sigma bonds? 20 sigma bonds. Now, there are no triple bonds in this molecule, so I don't have to worry about that. But there are some double bonds. Being that there are double bonds, we're going to count the double bonds one time for each one, and that will count the number of pi's. So 1, 2, 3, 4, 5. So how many pi bonds? There are 5 pi bonds. Okay? All right, so hopefully you should see that there are 20 sigma, 5 pi. What you need to do is draw the Lewis dot structure, and it's pretty simple to determine the number of pi and sigma bonds. Okay, all right, I am the Crazy Hat Chemist, and I am going to wear another crazy hat, and I'm not sure if this is really a super crazy hat, but this was my grandmother's hat from a long time ago, of course, okay, on my dad's side. Give me a thumbs up if you like that video, subscribe to my YouTube channel, and pass on my YouTube channel to all your friends and tell them to subscribe too. Tell your grandmother to subscribe, right? That's why I'm wearing my grandmother's hat. Have a great day. See you next time. Bye now.